Imagine reading a textbook right before an exam,
Okay.
but instead of just memorizing the words,
Yeah.
your brain physically rewires itself in like milliseconds.
Oh, wow.
Yeah, to become this world-renowned expert on the subject.
Mm-hmm.
And then the second the test is over, it just instantly reverts back to normal.
Right, which sounds like absolute science fiction.
Exactly.
Yeah.
I mean, it sounds completely made up, but for the AI sitting on your laptop right now, it's really just another Tuesday.
It is. And it completely upends the traditional logic of how we, thought artificial intelligence had to operate.
Yeah.
Because we're used to systems that require these immense glacial periods of time to learn anything new.
Right, which is the modern mystery we are tackling in this deep dive. So welcome.
Glad to be here.
If you're listening to this right now and thinking, I've used ChatGPT and it doesn't feel like it's training itself, you are definitely not alone.
No, not at all.
Our mission today is to demystify this exact illusion. We are pulling from a fascinating, honestly highly technical paper out of Google Research. It's titled Learning Without Training: The Implicit Dynamics of In-Context Learning.
It's a great paper.
It really is. We're going to peek behind the curtain of basically the ultimate magic trick. We want to reveal the hidden math that allows a large language model to learn on the fly without a single line of traditional retraining.
Yeah, because as we're going to discover, it's not actually magic at all.
Right.
The underlying mechanism is this highly rigorous, deeply elegant mathematics that's just happening in real time. But I think to really grasp why this paper's findings are so disruptive to computer science, we need to establish exactly how machine learning usually works.
Let's set that baseline, because when we talk about training an AI, we're usually talking about a massive, expensive dynamic optimization procedure.
Right.
We call it gradient descent. You feed the model millions of data points, say, pictures of cats.
Right, classic example.
Right. And it makes a guess, calculates how wrong that guess was, which is a metric called the loss. And then it physically updates its underlying numbers to be less wrong the next time.
And those numbers, the weights, they're essentially the artificial synapses of the neural network.
Okay.
Modifying those weights through gradient descent is the literal definition of training a model. I mean, it requires server farms, massive amounts of electricity, months of compute time.
Right. It's like studying for years to physically rewire your brain.
That's a great way to put it. But there is a hard line in the sand. Once that training phase is over, those weights are locked in.
It's completely frozen.
Yes. When you're chatting with a large language model at home, you're doing what's called inference. And at inference time, the model's underlying weights are frozen. They're a static, read-only file.
And I am struggling to reconcile that. Because if the brain is frozen, how does the prompt actually stick? Like, you sit down, you type a highly specific, totally bizarre prompt. Maybe you tell it to translate English into a made-up language where every word has to start with the letter Q.
Right.
And it just does it instantly. It follows your brand new rules.
Yeah.
Wait, if the weights are locked, how is it physically processing this new rule?
So what's fascinating here is that the researchers behind this Google paper hypothesized that the model isn't actually as frozen as we thought.
Really?
Yeah, they propose that this phenomenon, which is called in-context learning, or ICL, is actually a form of implicit fine-tuning.
Implicit fine-tuning.
Right. The AI is performing temporary invisible weight updates right there at inference time. It's reorganizing its internal representations based purely on the text you just gave it.
Okay, let's unpack this. Because saying the AI is performing invisible weight updates while its actual weights are frozen sounds like a paradox.
It does sound counterintuitive.
Yeah. We need to look under the hood. Where exactly is this happening inside the AI's architecture?
So, to find the location of this hidden learning, the researchers generalized the core component of a transformer model. And just as a reminder, the transformer is the architecture behind almost all modern LLMs.
Right, the backbone of all of this.
Exactly. So they defined what they call a contextual block. A contextual block consists of two specific layers stacked right on top of each other.
Okay.
First, you have a self-attention layer, and second, right after that, you have a standard neural network layer, specifically a multi-layer perceptron, or MLP layer.
So it's a 1-2 punch, self-attention, then MLP.
Right. And here is the major mathematical breakthrough of the paper. It's formalized as Theorem 2.2. They proved that the context, the prompt you typed in, actually transforms into a direct mathematical update to the MLP's weights.
Wait, it directly updates them?
Yes. It's what mathematicians call a low-rank update, specifically a rank 1 matrix update.
I want to make sure I'm visualizing this correctly. A rank 1 matrix update. What does rank 1 actually mean in like a physical functional sense?
Think of a rank 1 update, like putting a highly specific tinted piece of glass over a flashlight.
Okay.
You aren't changing the complex wiring of the flashlight itself. That wiring represents the frozen, pre-trained weights of the model.
Right, the stuff that took months to train.
Exactly. But you are passing all of its light through a single, focused filter, the rank 1 update. That filter temporarily changes the color and shape of everything the flashlight shines on, just for that moment.
Oh, that makes perfect sense. I'm not rewiring the flashlight. I'm mathematically intercepting its output.
Yes.
But why does this happen in the MLP layer? Why doesn't the self-attention layer just handle this on its own?
Well, previous research, specifically a foundational paper by Chen et al., proved that self-attention layers actually cannot compress context into exact weight updates without fundamentally altering the model's architecture.
Ah, okay.
If you tried to force the self-attention layer to hold the new rules, you'd have to add new biases and basically hack the system entirely.
So the attention layer is essentially the scout out in the field. It gathers the intel from the prompt you just typed, but it doesn't have the capacity to act on it alone.
That's a great analogy. The attention layer maps out how all the words in your prompt relate to one another, but it passes that map to the MLP layer, which is like the general strategy map.
And the scout's intel mathematically redraws the general's map on the fly.
Exactly. This new Google research paper proves that the MLP layer is naturally predisposed to absorb this context. In the architecture, the MLP acts like a massive key value store.
Key value store. Let's break that down for the listener.
You can think of the first matrix in the MLP as the keys, which are the triggers the AI looks for. The second matrix represents the values, which are the core concepts it retrieves.
Okay, so like a dictionary.
Kind of. If the key is the concept of apple, the value it retrieves is red fruit. The research shows that the prompt context implicitly transforms the keys to match your specific instructions, while leaving the core values unchanged.
Let me test this. If my prompt is, for the rest of this conversation, pretend an apple is a black skull.
Dark, but sure.
Right. So the original value of what a black skull is remains deeply embedded in the frozen weights. But the rank 1 matrix update, the tinted glass we put over the flashlight, intercepts the key.
Yes.
So now, when the AI sees the word apple, the trigger has been temporarily rewired to retrieve the black skull value.
That is a brilliant articulation of the mechanism. The prompt rewires the triggers, not the core concepts.
Here's where it gets really interesting to me.
Yeah.
Because you're not just uploading a prompt all at once like a zip file.
Right, it's sequential.
Yeah, when you interact with an LLM, you are typing it out. The AI reads it token by token, word by word. So as I'm typing a paragraph, is the AI essentially running a hyper-fast, invisible training simulation on itself with every new word?
It absolutely is.
Yeah.
And the researchers explicitly mapped this out in what they call Proposition 3.1, the implicit learning dynamics. They discovered that as the AI consumes those prompt tokens one by one, it performs an iterative process that perfectly mirrors online stochastic gradient descent.
Just to remind everyone, stochastic gradient descent is that massive trial and error math process, usually reserved for server farms, taking months to complete.
Yes.
And you're saying it is happening silently in the background of a single prompt in milliseconds.
Yes. Every single new token you provide acts like a fresh data point in a mini training run.
That's wild.
It is. When the AI processes a new word in your prompt, it calculates how much the specific word changes its understanding of the task. It generates an invisible loss and a metagradient. They call this the marginal effect.
Metagradient, meaning a gradient about the learning process itself.
Right.
Let's ground this in a real example. If I type translate this to French, the word translate generates a huge metagradient because it sets the entire structural task.
Exactly.
And French generates another massive gradient because it specifies the target language. But what happens if I start rambling?
What do you mean?
What if I add, please make sure to do a really good job because my boss needs this for a meeting on Tuesday?
The math actually accounts for your polite rambling beautifully.
Oh, really?
Yeah. The researchers found that as the model processes more of the context and converges on a solid understanding of your rules, the gradient updates actually vanish.
Wait, they just stop?
Basically, yeah. If a new word in the prompt adds no new mechanical meaning, like your notes about your boss and Tuesday, the marginal effect drops to 0.
So the implicit weight update becomes 0.
The model has mathematically learned the rule you want it to follow. Once that happens, it stops updating its internal map. The rank 1 matrix filter is complete.
It literally stops paying attention to the fluff once the mathematical patch is built.
That is fascinating. Did they test this on other types of AI architectures, or is this just a quirk of transformers?
They tested this implicit learning dynamic on recurrent neural networks, or RNNs, as well.
Okay, and how did that go? Well, they found that RNNs were much less stable. The gradient updates in an RNN failed to converge smoothly as the context grew. The metagradients just got chaotic and noisy.
Ah, so it couldn't hold the context.
Right. This highlights exactly why the specific combination of the self-attention layer and the MLP in a transformer is so special. The transformer creates a uniquely stable environment for this invisible training to occur word by word.
I have to admit, I'm going to play the skeptic here for a second.
Go for it.
This all sounds incredibly elegant in theory. The math adds up on a whiteboard. Proposition 3.1, Theorem 2.2, rank 1 matrices. But how on earth did they prove this experimentally?
It's a fair question.
Because how you actually measure an invisible weight update inside a frozen model without breaking it?
They designed a highly controlled experimental setup involving linear regression. They trained a simple transformer from scratch specifically to solve linear regression tasks.
Which is essentially drawing a line of best fit through a scatter plot of data points. The very classic, mathematically pure machine learning problem.
The purity is key here. It's not fuzzy like human language. You can see the exact weights needed to define a line. So they compared two very different scenarios.
Okay, what was scenario 1?
In scenario 1, they gave the normal frozen model a prompt filled with data points, the context, and asked it to predict the next point. It did this perfectly, utilizing the in-context learning we've been discussing.
So that's just the standard AI interaction. What was scenario 2?
In scenario 2, they gave the model zero context, no prompt with data points at all.
None.
None. Instead, they manually reached into the model's MLP layer and explicitly patched the weights using their theoretical rank 1 formula.
Whoa.
Yeah, they took the formula, which they denote as T sub W plus delta W, and surgically implanted the mathematical knowledge of the prompt directly into the weights.
So they manually applied the tinted glass to the flashlight.
Exactly.
And what happened when they asked this patch zero context model to make a prediction?
The outputs of the two models were absolutely identical. And they weren't just close. The predictions matched up to an incredibly precise order of magnitude, a difference of 10 to the negative 7th.
10 to the negative 7th. That is staggeringly precise.
It is.
The output of the model, naturally reading the prompt, is mathematically indistinguishable from a model whose physical brain was manually rewired using their equation.
Right.
That moves this from a neat theory to hard, undeniable proof.
It proves the AI is not just retrieving old memorized capabilities from its pre-training, it is genuinely learning in real time. And to hammer this home, the researchers took it a step further.
What else could they do?
They compared the direction of these implicit weight updates against the updates from real traditional fine-tuning using gradient descent.
Wait, how do you compare the direction of invisible math against real training?
They used a metric called the normalized Frobenius inner product.
Okay, wait. Normalized Frobenius inner product. For those of us who haven't taken advanced linear algebra recently, you just mean they measured the exact angle and distance of the updates to see if they pointed in the same direction.
Right. That is exactly what it means, yes. They measured the geometry of the learning, and they proved that the invisible updates from the prompt and the real updates from traditional fine-tuning push the model's weights in highly aligned directions.
Wow.
The AI is doing the exact same structural work, just through temporary means.
Let's zoom out. We have this incredible mathematical proof that in-context learning is actually real-time, rank 1, implicit fine-tuning.
Right.
How does this actually change the future of AI? The paper details 5 massive implications, and I want to look at how they cascade into one another, because this changes everything from how developers build models to how you and I type prompts at our desks.
Definitely. If we connect this to the bigger picture, if we can mathematically prove the AI is learning on the fly, that completely changes how we fix these models when they break.
Okay, how so?
Well, in the AI research world, there's a field called model editing. Developers have been building complex techniques with names like steering vectors and the ROAM or MEN protocols. The goal has always been to try and force models to forget bad information or learn new facts without doing a full, expensive retraining.
Like trying to perform inception on the AI to surgically change a specific memory.
Exactly. But this paper proves that those highly engineered manual hacking techniques are actually just replicating the exact same mechanism the model uses naturally every time it reads a prompt.
Seriously.
Yes, it unifies the entire field of in-context learning and model editing. Model editing isn't a hack anymore, it's just manually triggering the AI's natural adaptation instinct.
And if we don't have to guess how to fix them, it means we don't have to guess how to talk to them either, which transitions us right into prompt engineering.
Right.
Because right now, writing a prompt is basically voodoo. We add phrases like, take a deep breath, or think step by step, because it empirically seems to work, but it's pure trial and error.
Now, we have an explicit formula. The researchers showed that textual concatenation, putting words together in a prompt, literally equals mathematical operator composition in the weight space.
That's amazing.
It lays the groundwork for moving prompt engineering from a dark art to a formal, predictable science. You could theoretically calculate the optimal string of tokens to induce the exact weight update you want.
Which leads right into solving one of the biggest headaches in AI right now, hallucinations. If we understand the math of the prompt, can we use it for mechanistic interpretability?
We can absolutely use it as an early warning system. Remember those meta-gradients we discussed? The marginal effect of each new token?
Yeah, the invisible loss it calculates.
Right. Because we can now track those invisible gradients dynamically, we can monitor the stability of the AI's internal learning.
Oh, I see where this is going.
If the model starts generating a response and the implicit gradients suddenly spike erratically or fail to converge, it's a real-time mathematical signal that the model is hallucinating or experiencing mode collapse.
It's an invisible lie detector built right into the math. We could catch the AI losing its mind before it even finishes typing the sentence.
Exactly. And this level of insight doesn't just change how we use models, it changes how we build them. For model design, if we now know exactly how this learning happens, that it relies heavily on the contextual block of self-attention and MLP layers, we don't have to guess at architectures anymore.
We could just use the math.
We can mathematically evaluate which new architectures are actually best at implicit adaptability. As researchers design the next generation of AI, they can use this framework to guarantee the architecture supports robust in-context learning.
But there is one final piece to this puzzle that honestly sounds a bit like science fiction.
Yeah.
Context compression.
Oh, yes. The holy grail of efficiency.
Because right now, if you want an AI to analyze a massive 100-page legal document, you have to paste that entire document into the prompt every single time you ask a question.
Right. And the AI has to reread and reprocess all those tokens, computing the self-attention over and over. That requires massive amounts of compute and money.
But if the prompt is ultimately just generating a mathematical update to the MLP weights,
why compute it over and over?
Exactly.
The implication is that we could take a long prompt, run it once, extract the resulting static weight update, that T sub W plus delta W patch, and just save it. You could reuse that compressed context endlessly without ever having to process the original text again.
So what does this all mean? Let me make sure I have this right. It's like saving a highly complex custom photo filter.
Okay, I like that.
Instead of manually moving 50 different sliders for brightness, contrast, and saturation, which is the equivalent of processing a massive prompt token by token every single time you want to edit a picture, you just save those final slider positions as a single filter.
Right.
Then you apply the mathematical filter instantly to any new photo.
You are caching the intelligence, not the text. While the paper notes that the exact updates currently depend dynamically on the query token, they suggest that aggregating or averaging these updates could produce a static, universally applicable patch. It would save untold amounts of computational power.
That is just incredible. So to quickly summarize our deep dive into this Google research paper, in context, learning is not magic.
No.
It is not an illusion. When an AI learns a new rule from your prompt instantly, it's utilizing standard neural networks to transfer your context into a temporary, low-rank update of the MLP weights.
Exactly.
It's executing a hidden, invisible gradient descent, word by word, rewiring itself on the fly without ever altering its permanent training.
This raises an important question, though. A broader, perhaps more philosophical question that extends far beyond the architecture of a machine.
Oh, where are we taking this?
Think about what we just unpacked.
Right.
We have proven that human language, specific instructions, and context can be explicitly mapped as precise mathematical weight updates.
Right.
Words temporarily rewire an artificial brain. It creates a measurable physical change in how the system processes reality.
Yeah.
If human communication acts as a rank 1 metagradient on a machine, does it act the same way on us? When you listen to a persuasive argument, or when you read a compelling story, are those words acting as real-time metagradients? Are they physically, temporarily altering the synaptic weights of your own mind before you even fully realize you have learned something?
That is going to keep me awake tonight. The idea that every conversation we have is an invisible gradient descent, updating the matrices of our own minds.
It's a lot to consider.
It really is. Something to think about the next time you read a prompt or a paragraph.